Good morning, everyone. Uh, my name is Aranya Aumit Paul. I'm a PhD student in the Construction Management Department of Louisiana State University. Currently, I'm working with Dr. Ali Kazimi's team. And today, I'll be talking about my ongoing research towards sustainable robotic construction, that is, the concrete 3D printing with Quarry byproducts and low Portland cement content. So, let's dive into the extrusion-based construction 3D printing. Imagine a robotic arm precisely laying down layers of concrete, digitally guided to build a structure from the ground up. That's the essence of the transformative technology. Now, why is this so exciting? First, it promises faster automated and construction, reduces the need for manual labor, and second, 3D printing unlocks the incredible design freedom, allowing complex and impossible shapes with traditional methods. That is not can be done. Third, imagine a clear, more compact construction site. 3D printing minimizes the space for needs. We can have reduced waste material for this 3D printing that is required for the conventional concrete technology. Even better, this technology reduces waste material, only what's needed is used. Studies show significant energy savings, making it a lower environmental impact, helping reduce the greenhouse gas emission within our industry. But the problem don't stop there. You might think that using more cement means stronger structure, but that's not always the fact. It actually increases the chances of shrinkage during the curing process. This leads to cracking, weakening the overall structure. Additionally, high cement mixes can be more vulnerable to attacks from chemicals in the environment, reducing the long-term lifespan of the 3D printed cement. So you can see simply throwing more cement at the problem isn't the solution. Now, let's look at some real world data. This chart compares the cement content used by different researchers in 3D printing projects. As you can see, there is a wide range represented here from 600 to 1240 kilogram per meter cube. This verification underscores the significant point there is currently no single industry standard for cement content in 3D printing mixes. This presents both a challenge and an opportunity. So, one promising strategy to reduce the cement reliance is incorporating recycled concrete aggregates. Traditional concrete demolition generates vast amounts of waste by crushing the old concrete. We can reuse it as aggregates, lowering the need for newly mined minerals. As you can see, researchers have successfully used RCA in both 3D printing by using 600 kg per meter cube of cement and traditional casting methods like 162 kg per cubic meter of cement. This demonstrates the feasibility of reducing cement while maintaining the structural integrity. To push sustainably further, let's look at the particle packing optimization. This idea is to carefully select aggregates for different sizes to fill the space within the concrete mix as efficient as possible. Various models help us with this. Think of these theoretical blueprints as the optimization curves. Curves like those from Fuller and Anderson help us design mixes with a wide range of particle sizes for optimal density. By calculating packing density, we directly measure how tightly our materials pack using bulk density. We can also calculate how much of each material to use by weight to achieve our desired density. Discrete element model, we model virtual particles of different sizes and shapes, seeing how they pack together. This helps refine our mixes beyond basic optimization curves. And compressible packing model is an advanced model that takes into account how particles deform slightly under pressure. It gives us even more precise in predicting real-world packing behavior. Another powerful approach is a portion of Portland cement with supplementary cementitious material. There is a few SCMs in the industry. For example, fly ash, slag cement, silica fume, blast furnace slag. We all know about that. These are often industrial byproducts that would otherwise end up in landfills. Here are some widely used SCMs we can see, like fly ash as a byproduct of coal-fired power plant, steel slag, a waste material from steel production, and we can researchers also have used combinations like SCMs with slag, fly ash, metakaolin, and limestone, seeking the optimal blend for specific performance needs. For our project, our objective is to incorporate the Quarry byproducts and the pea gravel along with the dense particle packing, and our goal is to 3D print all these Quarry byproducts and pea gravel dense packing and the comprehensive performance evaluation of the printed materials. For our project, we have got 3 byproducts from a local industry of Louisiana that is completely unusable to them. So we decided to test their properties and incorporate them with the coarse aggregate, that is pea gravel, for our project. And the pea gravel is not larger than 9.5 millimeters in size. For the method, we have picked Fuller and Thompson model and the modified Anderson curve, and it works with the sieve size and percent passing. So we have taken as the standard curve, and we have compared our model to these curves with the particle diameter that we have measured, and the parameter is basically optimized by the Q that is adjusted by the curve of fineness and coarseness. For the packing density, it was also taken as a method, and we have got the bulk density, as I mentioned before, that we can get the void content that is found in the packing, and when we multiply with the specific gravity and the weight fraction, we get the packing density. And from the packing density, we can also get the void content, which can be calculated as the cement paste. And from that cement paste, we have found the amount of cement and water, and the amount of limestone, we have already fixed that for our cement paste. And in the volume of aggregates, we have found the coarse aggregate and the fine aggregate percentages, comparing it with the optimization curves. So here we can see the comparison with optimization curves for different combinations of pea gravel with 3 types of sands. We have compared all our sieve sizes for the sands, the Quarry sands and the pea gravel with the combination of Fuller and Thompson curve and the modified Anderson model. So we have taken into evaluation for the 65% of one sand of each sand, and 35% of the pea gravel, that is the coarse aggregates, and we have ranged it to like 70% and 75% and vice versa. From the previous model, we have found the highest packing densities for each type of Quarry aggregates, that is the Quarry sands and the pea gravel, and we have found the 70% and 30% range for the shaker and pea gravel, 65% and 35% for the Indian village field sand and the pea gravel, and also for the Independence field sand and the pea gravel, we have found 60% and 35% for the highest packing. And with the highest packing curve, we have calculated the packing density from the bulk density calculation, and here we have found that the numbers matches with the optimization curves. Now we have tested our packing design, we have tested the mixture, and for the first one we have tested the highest packing for the shaker sand and the pea gravel. So here the packing density was 75%, so the void content was around 25%. So we have tried the cement paste, but the cement content was lower. It was 353 kg per cubic meter, but the mixture was not printable. So we found out a way to make it printable. So, but the cement content that is showing that we got for the printing, it was not successfully covering our cement content goal. That was lowering the amount of cement which is below 400 kg per meter cube. So you can see the printing here, the printing samples. The layers, the surface finish is not good. Also, the layers are deformed for this part. So this sand is not printable according to our goal. For the next one, for the independence fill sand and pea gravel, we have mixed around 65% and 35% of pea gravel, and the packing was 72% for the aggregates, and the 28% was the cement paste. So for this one as well, the amount of cement content we have got from the void content, it was not printable because the material was too stiff. Then we have added some limestone. Also, we have increased the water content ratio to make it a little bit printable, and it was successfully covering our cement content goal, which was below 400, and it was 388 kg cubic per meter. And the problem was with the structural properties, and it didn't retain its shape because you can see the bottom layer was ½ inch and the second layer was a little bit extra than our expected results. So this combination of mixture was also not printable for us. And for the next part, we have tried the Indian village fill sand and 35% pea gravel, and we got the packing density for like 70%. And here, the cement content that we have got was like 392 kg per cubic meter, and with no limestone, it was not printable as well. For making it printable, we have used some limestone and increased the water content ratio, and you can see the results are here. So we have got like uniform layers with the printing, and it satisfied the shape stability. Also, it satisfied our cement content goal that was below 400, which is 395 kg per meter, cubic meter, and the result is printable. So, by this results, we have come to a conclusion. We need some additional constraints related to this printability. We need to maintain the flowability of the cement paste. We need to ensure the water cement content ratio, and we need to satisfactorily maintain the structural properties so that it maintains the mechanical strength after printing the specimens. And for the next steps, we are trying to optimize this mix design and maintain our cement content goal with that packing density we have got from the optimization curves as well as the packing density calculation. And also after that, with that packing density mixture, we are trying to print that material and test its mechanical properties with low cement content. Our project is sponsored by Louisiana Board of Regents and supported by the National Stone, Sand and Gravel Association and Louisiana Concrete Association. And the collaborators are Dr. Hadi Rashidi, Michael Dumoy, and Garrett Tegri. Thank you.